Let's talk about factoring. Factoring is one of those things I see students really struggle with at the start. In fact, if you don't just sit down and practice it and get really good at it, I see students continue to struggle with it into calculus, and by the time you get to that point, you're just going to be too far behind. So it's really an important skill to sit down and just make sure that you're comfortable with, and it just does take practice. It takes doing a lot of examples. So let's talk about kind of the keys to successfully factoring in this video, and we'll do a bunch of examples too. So the first thing we always want to look for is to find the greatest common factor. It will always be easiest to factor out a greatest common factor first. Sometimes that might be all that factors out, but even if we're going to use one of the other methods, factoring out that largest thing first just makes the whole problem a lot easier. Next, we're going to pay attention to the number of terms the expression or the polynomial has. 2 terms, 3 terms, or 4 terms. If there are 2 terms, we're going to look to see if it's the sum or difference of squares or of cubes. If it's the sum of squares, it is prime. We can't factor it. It's done. If it's the difference of squares, we can factor it. A squared minus b squared equals a plus b, a minus b. And whenever we factor, we can always check these things by multiplying them back together. Most of the time, we're very comfortable with multiplication, and so we know how to multiply something like this. We distribute, or we can say we FOIL it. So we'd have a times a, which is a squared. A times a negative b is a negative ab. B times a is a positive ab, which is why there's no ab term here. And then finally, to get b squared, b times a negative b gives us that negative b. And so by having the signs different, those middle terms cancel when it's a perfect square. Next, we have the sum or difference of cubes. These can always be factored. So unlike with squares that we can't factor the sum of the cubes, we can always factor. So if we have a cubed plus, and that should be a b cubed. If we have a cubed plus b cubed, well, we can factor that as a plus b, and then a squared minus plus ab plus b squared. So let's talk about these signs for a second, because I had a plus minus here, and then a minus plus here, and that is correct. So the way we can remember the signs is the signs stay the same, they switch, and they're always positive. So if you start with a positive in between those cubes, you're going to use the positive at first, you're going to switch it to a negative, and then you use a positive always. If you start with the minus, then you use the minus here, and then you use the positive next. So the order of the signs matters, and the reason we see that minus plus there is because if we're using the top sign, we continue to use the top sign, the bottom sign, we continue to use the bottom sign. So we'll see examples of that in this video too. There are 3 terms we need to factor that into 2 binomials, so any trinomial factors into 2 binomials. Keys being the first term of the trinomial is the product of each of the first terms of the binomial. The third term of the trinomial is the product of the second 2 terms, and then the middle term of the trinomial is the sum of the outer and inner products. That is, if it is in the correct order. So we'll discuss that as well. But the key we want to see with trinomials is you have your variable squared term sitting first, your single variable term, and then finally your constant term. So we'll take a look at that. And then finally, if we have 4 terms, we're going to factor by grouping. We're not going to concentrate on anything beyond 4 terms. So let's just jump right into an example. So here we have an expression. It's got 3 terms, 5a squared times a b cubed c minus 15a squared b to the 4th c to the 5th plus 20a cubed b cubed c cubed. Now, there are 3 terms, but I'm not going to look down here yet, right? I'm not going to look at how many terms I'm looking at. I'm going to look for that greatest common factor first. That's going to be the first thing I care about. So let's start with the number portion, the numeral. So I have a 5, a 15, and a 20. What goes into all of those things? Well, 5 goes into all of them. And let me leave myself some space. So I'm pulling this out of the parentheses, I'm factoring it out. I'm going to have an a, b, and c term here, so I'm going to leave a little bit of space, but I'm just going to work with the numerals first, the numbers first. So if I pull a 5 out of 5, it's just a 1. I don't need to write that 1 because I'm going to have other things there. If I pull a 5 out of 15, I'm going to have a minus 3. If I pull a 5 out of 20, I'm going to have a plus 4. And notice I'm leaving space again because I'm going to have the a's, the b's, and the c's in there. So let's see what we have with the a next. So I have an a squared. I have an a squared here, and I have an a cubed here. So what goes into a squared, and a cubed? Well, a squared goes into all of those things. I can't take out the a cubed because there's not enough a's in the first 2 terms. So if I take a squared out of an a squared, there's nothing left. So again, we still don't have anything here other than just a 1. I don't want to forget about that 1. It is there, but I think I'm going to have some other things coming up. 15, we took the a squared out of that as well. So now there's just a 1 here. so I don't need to write that negative 3 times 1 or just negative 3. Then we took the a squared out of the a cubed, meaning I do have an a there. Next, we're going to move on to the b terms. See a b cubed, a b to the fourth, and a b cubed. So I'm going to pull out the b cubed. Well, I pulled out all of those b's there, so I have still that 1 here. So I have a 1 from the 5, a 1 from the a, and a 1 from the b. 1 times 1 times 1 is just 1. Then I take a b cubed out of a b to the fourth. That leaves me just a b. And then b cubed divided by b cubed, I have just a 1 in that last position as well. Finally, I'm going to look at the c's. I see that everything has a c, but this one only has a single c, so I'm just going to have to write the single c there. Now, because I factor out everything from this first term, and it was the whole term, I do need to remember to put a 1 there. If I'd had, say, a c squared here, I would have had a c here, but because there wasn't, there's just going to be a 1. Then we took a c out of a c to the fifth. That leaves us c to the fourth. And we have a c taken out of a c cubed. That leaves us c squared. And so now, this is my polynomial. If I look to factor that in further, this is the greatest common factor. We can't do anything else with that. We factored all of that out. It comes out of everything. Even though we have 3 terms here, there's not going to be any way for me to factor this further. I have a c squared term here. I have a c to the fourth term here. So somehow I'd have to be using c squared as one of my first or third factors. And I can't use that with the b, so at this point I'm done. This is fully factored. This would be my answer. And so we'll practice with those trinomials a little bit more, and hopefully we'll get a better hang of it. But this, we can't factor that trinomial any further. Next, let's move on to number 2, something with 2 terms here. So 2 terms, I see a minus in between. It better be a difference of something if it's going to factor. And so 9 is a perfect square, and x squared obviously a perfect square. 16 also a perfect square, so I'm pretty sure I can factor this into the difference of squares. And so the square root of 9 is 3. The square root of x squared is x. Those will be our first terms. The square root of 16 is 4. And so I'm going to put those as my second 2 terms, and then the last key is they have to have opposite signs, a plus and a minus. And that's it. That's done. Just very formulaic. You take the square root of the first, square root of the second, and that gives you your factor for the difference of squares. Again, with any of these, we can multiply them back together to check, and I do recommend that until we really get comfortable with them. And in fact, anytime I factor a trinomial, I always multiply it back together just real quickly in my head, just to make sure it works, because they're so easy to mess up or to make a little mistake. So just a quick little multiplication: 3x times 3x, 9x squared. 3x times negative 4 is negative 12. 4 times 3 is a positive 12. That cancels out the x term. And then 4 times a negative 4 is a negative 16. So we have that right. All right, let's look at number 3 next. And let me just actually tinker with this for a second. I want it to look a little different, get a slightly different result. Let's say we have 9a squared plus 100b squared. So once again, we see that we have 2 terms. I should also note the reason I changed this is we should always look for the greatest common factor first. So 9 and 16, there was no common factor. 9 and 100, a and b, no common factors there either. So let's go ahead and see what we can do with the 2-term polynomial then. If it's 2 terms, it's going to have to be that sum or difference of squares or cubes. The square is kind of indicating to me it's probably going to be a square. And so we have a sum of squares, 9 and 100 both perfect squares. And so remember what we said about the sum of squares? Can't factor it, it's prime. At least we can't factor it in the reals. We can factor it in the imaginaries, but we're only going to concentrate on factoring in the reals. So if we see that sum of squares, we're done. We just say it's prime. Let's move on to number 4, 27x cubed minus 8. Again, I'm going to look for the common factor. 27 and 8, there's no common factor there. Obviously, only one term has the x, so no greatest common factor. And we see we have 2 terms, so it's going to be hopefully a sum or difference of squares or cubes. Otherwise, we're kind of stuck. And the x cubed, pretty good indication we're going to have a cube. So like I said, that exponent kind of giving away what we're going to have. Now, we might have higher powers that are still cubes or squares. We'll see an example of that a little bit later. But for these smaller ones, pretty dead giveaway, we have hopefully a cube here. So 27 is a perfect cube, 3 times 3 times 3. 8 is a perfect cube, 2 times 2 times 2. So I'm going to write out a little bit more on this one than I did for the sum and difference of squares. I'm going to define the a and the b. So the a is whatever that first term is before it was cubed, or the cube root of this thing right here. So the cubed root of 27 is 3. 3 times 3 times 3 gives me 27. And the cubed root of x cubed is just x. Cubed root of 8 is 2. And so now I'm just going to use the formula. My formula says I have to have the a and the b, so 3x and 2. And they're going to be separated at the start with whatever the same sign was, so the minus. And then we take our a and we square it. So if we square the 3x, we get a 9x squared. Then we use the opposite sign of whatever we did before, so now it's going to be a plus. We multiply the a and the b, so 3x times 2 is 6x. And then we always use a positive. We square our b, which will be 4. And that's it. That's our answer. So we first write down the a, the b with the same sign as what we started with. We square the a, we use the opposite sign. We multiply the 2, we always have a positive, we square the b. And the second portion here, that should never factor. That'll always be prime, so we won't go any further. That is it is a trinomial, so we might think, hey, could I factor that a little bit further? And no, we can't. All right, let's move on to some trinomials that hopefully will factor. So we'll start with number 5 here, x squared plus 5x minus 6, 3 terms here. So this is, I think, the most complex form of factoring. We have to think about the first term, the last term, and then the outer and inner product. And so before I do this problem, let me just kind of remind ourselves, let's remind us how we multiply these trinomials. So let's say we have 2x minus 1 and an x plus 3. So when we multiply these together, we'd have 2x times x. That's 2x squared. We'd have 2x times 3, which is 6x. We'd have the negative 1 times the x is negative x. And then the negative 1 times 3, which is 3. So we saw that we had the first terms multiply to that first position. The last terms multiply to, and I did that sign wrong, that should be a minus 3. Not a plus 3, but a minus 3. So double checking myself, but when we multiply those, they multiply to the last position. And then those middle terms, we'll get a 6x minus x, which is a positive 5x. Those come from the outer and the inner products. And so those were the instructions that I gave you. The first term of our trinomial, to write this out formally, we have the 2x squared as our first term. We have that 5x as our second term. And then we have the minus 3 as the third term. The first term comes from the product of the first two terms of the binomial. The last term comes from the product of those last two terms of the binomial. And then the middle term is the most complex to get to. We get that from the outer and the inner products being added together, so 5x there. So we're going to apply that logic in kind of reverse. We're going to do it backwards. So I know that if this thing's going to factor, it's going to have to factor into a pair of binomials. So I might as well write it down, the two sets of parentheses. The first term in this case is relatively simple. X squared has to be an x and an x. That's the only way we can get to an x squared. And then the factors of 6. Well, this is a little bit more complex. So off to the side, I'm just going to write down a little bit of scratch work. The factors of 6 are 1 and 6, or 2 and 3. Now, I've also ignored the sign completely. It's a negative 6, so it could be a positive 1, negative 6, negative 1, positive 6, positive 2, negative 3, or negative 2 and positive 3. So a lot of different possibilities there. But I'm going to ignore the sign for a second. I'm just going to worry about these pairs of numbers. And I'm just going to start by penciling a pairing in. So just to show you something that wouldn't work, I'm going to start by penciling the 2 and the 3. So I already know what it's going to look like because, like I said, the more of these you do, the better you get. So if you practice tons and tons and tons, it becomes just automatic and you can recognize them pretty quick. But if I have the 2 and the 3 in there, we know that the first term and the third term will work out properly. Those will be correct. But it's that outer and inner product we got to pay attention to get to the 5. So here, for the outer product, we get a 3x. For the inner product, we get a 2x, and that seems really promising. That would give us 5. But we also have to think about those signs. So if I want to get a negative 6, that means one of them has to be a positive and the other has to be a negative. If that second term is negative, these signs will be different. Versus if that second sign is positive, the signs will always be the same. So because our signs are going to be different, that means I'd have a positive 3 or a negative 2, or a negative 3 and a positive 2. Either way, we're going to be subtracting those values. So if that last sign is negative, that tells me these signs are going to be different, and we have to subtract these two values. Is there any way for me to subtract 3 from 2 or 2 from 3 to get a 5? No, there is not. So what that tells me is I've chosen the wrong pairing. The 2 and the 3 aren't going to work. So now I'm going to switch it to the 1 and the 6. So once again, I'll do the outer and inner products. I have a 6 times an x and a 1 times an x. That is a 6x and a 1x. Well, is it possible for me to subtract these two things to get to a 5? Absolutely. I need it to be a positive 5. So what that means is I need the positive to be on the 6 and the negative to be on the x. So keeping the sign with their respective outer inner products, if the 6x has to be positive, this 6 has to be the positive. If the negative x, or if the x has to be negative, the 1's going to be the negative. And so now we have it factored. So a little bit of checking and guessing, and there are different ways to do these. I know some people will teach you the box method, or there's all these crazy AC methods. I don't really care for them. I prefer just to learn how to factor the thing. What I do is a little bit of checking and guessing, and so it's nothing too complex. It's just thinking about those factors and then figuring out which ones can add, subtract to my given desired value. Now, I do have a little bit of a shortcut for it. So I started with the 2 and the 3 incorrectly. Typically, if that number in the middle is really, really large compared to the outer, that last number, I would choose the more extreme numbers here. So 5, not really, really large compared to the 6, compared to the outer 6. So if I didn't really know what it was going to look like, I would have started with the 2 and the 3 just as a guess. As that number grows, so if I'd seen something like maybe 7 there, well, I'd definitely be wanting to start with that 1 and the 6. So the larger that middle number is, that leads me a little bit further up the food chain to look for those numbers that are further apart. So we'll do some more practice with these. Let's look at number 6. I have a 6x squared, a 16x, and an 8. So if I want to jump right into it, we can. And I'm going to do this to show you it's harder, and then we'll come back around to an easier way to solve this. So the factors of 6, we've already said 1 and 6 and 2 and 3. Factors of 8, 1 and 8 and 2 and 4. So if we think about all the possibilities we have now, they're all positive, which makes it a lot easier. We know that because this is positive, the signs will be the same, and then they are both whatever this one is. So all the signs will be positive. We can go ahead and pencil that in. We know we're going to have a pair of binomials, and it's going to be a plus in between. But it still leaves me a lot of possibilities to try. The 1 and 6 could work with 1 and 8, or it could work with the 2 and the 4. The 2 and the 3 could work with the 1 and 8, or the 2 and 3 could work with the 2 and the 4. But I could also switch it. It could be a 1x and a 6x, and it could be a 8 and a 1. So I have a lot of different possibilities here to try. I'm going to look at that center number to try and use my shortcut a little bit here to speed me up. 16 is not relatively huge compared to the 8 and the 6. So I'm going to start with the pairings that are closer together. I'm going to start with that bottom line first, and we'll see how we do. So I'm going to pencil in the 2x and the 3x. And again, I'm penciling these in because I'm not sure they're going to work. So I'm going to write them in blue at first. So then my factors of 8, I'm going to start with the 2 and the 4. So I'm going to put a 2 here and a 4 here. I know that the first and last terms are right. We chose those numbers based on the factors. So we know those are right, but let's look at what the outer and inner sums are going to give us. 2 and 4 is an 8. 2 and a 3 is a 6. Well, 8 and 6 is never going to give me 16. So we have a problem. That's not going to work. So before I give up on it, we found that 2 and 4 don't work with 2 and 3, but that's if we use that set order. What if I were to switch these? What if I were to make it 4 and 2? So we can't just give up on them one time because the order matters. The 2 last time was hitting off the 4 and the 3 was hitting off the 2. If we switch that, we're going to get a different result. So 2 times 2 is 4 and 4 times 3 is 12. And do 4 and 12, both with x, does that give us 16? Yes, it does. So now I do know that I have the right pairing. This is the correct factorization. So we got a little bit lucky that those numbers closer together worked. If we'd started with the 1 and the 6 and the 1 and the 8, like I said, we would have had a lot of options to try. We would have had to go through the 1 and the 6, the 1 and the 8, then the 1 and the 6, the 8 and the 1. then the 1 and the 6, 2 and 4, 1 and 6, 4 and 2. Then we'd finally get to eliminate the 1 and the 6 and move on. In this case, we got there a little bit faster. So just to write out what our answer looks like, 2x plus 4 and 3x plus 2. Now I did tell you this one we could have been a little bit faster with if we'd recognized and paid attention to our very first step, which is to look for a common factor. There is a common factor in this example. Everything is divisible by 2. Everything is even. So I could have started by saying, well, let's pull out the 2. And when we pull out the 2, we have a 3x squared, and we have an 8x plus 4. Doesn't mean I get to stop because I can factor this now into a pair of binomials. And really here I wasn't done either, so let me come back and talk about that in just a second. So now my numbers are a little bit smaller. I have the 3 and the 4 I need to worry about the factors. So if we think about 3 and 4, 3 the factors are just 1 and 3, so we only have one option, which is nice. 4 the numbers are just a little bit smaller, 1 and 4 and 2 and 2. So we've really reduced the number of possibilities. I know that 1 and 3 are going to be involved. I'm not 100% sure on those second factors. So let's try the 2 and the 2, and when I plug those in, I'd get 2 times x is 2x, and then 2 times 6, 2 times 3 is 6, and 6 and 2 give me 8. So I'm not writing out those inner and outers this time, but we get the correct answer, and so this is my answer. So just a second ago, I said I really have to come back and talk about this. This wasn't done because our instructions were to factor. We did factor into a pair of binomials, but this is not completely factored. Because if we notice now, in these two terms, there is a common 2. And so we could factor that, and we get to the same answer. We'd pull out the 2, and we'd have an x plus 2 left over. And so we do get to the same factor. But notice, not only did we make our life harder by not pulling out that 2 to start with, it's a much harder problem, we also overlooked the fact that we could pull that 2 out, so we didn't have it completely factored. So it is always easiest to look for that common factor first. Let's move on to one last example with trinomials for right now. Let's take 6x squared plus x minus 12. So again, this is 3 terms, so we can factor it using our pair of binomials. And we have the factors, we're going to need the factors of 6 and of 12. Factors of 6, 1 and 6, 2 and 3. Factors of 12, 1 and 12, 2 and 6, 3 and 4. So we really have a ton of options this time. And the other thing that makes it a little bit trickier is that we don't know that the signs are the same. In fact, the signs are going to be different, and that always makes it a harder problem. Let me space that out a little bit better. So we'll have some number of x for our first term. We'll have some number of x for our first term of our second binomial. And I'm going to start with those closer together numbers because x is relatively small compared to the 12 and the 6. So I'll start with a 2 and a 3 here. Then I'll go on to the 3 and the 4. And let me start using blue just to show that I'm kind of making some guesses and we might have to move some things around. So my outer product would be 8x. My inner product would be 9. And I know the signs are different, so I'm going to have to subtract these two values. Is there a way for me to get down to that 1? Yes, there is. The 3 has to be the positive and the 4 has to be the negative because we need that 9 to be a positive and the 8 to be the minus, and that will give us just the 1x. And so just like that, we have it. That one kind of lucked into because they were those closest together pairings. We know the order 3 then 4. And so that's one of those things that if you can make those educated guesses, we are checking and guessing with these trinomials, but if we can make some educated guesses along the way, then we can sometimes get to those factors a little bit faster. Is that always guaranteed to work out? No. Could I have had it in the wrong order? Absolutely. But it worked out to be a little bit faster for us on that example. Number 8, here we have 4 terms. I should also note that there is no common factor. So 4 terms, if I want to factor something with 4 terms, I'm going to have to use factoring by grouping. So what we're going to do is we're going to group these first 2 terms and then these second 2 terms. So if I group those first 2 terms and look for what I can factor out, I see that both have x squared in common. So I'll pull the x squared out. I'm left with an x minus 3. Then I'm going to look at the next two terms. What do they both have in common? A 4. So I'm going to pull out a 4. If I were to pull out a 4, I'd have a negative x and a plus 3. That's a problem. Because right here, these two things need to be the same. If I'm going to factor this all the way down using grouping, these two need to be the same. So notice both the signs are wrong. So what that tells me I really should have done is I should have factored out negative 4, and that's going to switch these signs in here. Factor out the negative 4, then we have negative 4 divided by negative 4, just 1x, and 12 divided by negative 4, a negative 3. And so now these in parentheses, now with the blue underlines, they are common. So we're using almost that greatest common factor idea, but with the pairs of numbers and then across the two new terms that we've created. So x minus 3 becomes the common factor, and x squared minus 4 is left over when we pull it out. The same way we did on number 1. We pull this out of the first term, we're left with an x squared. We pull it out of the second term, we're left with that negative 4. Now there's actually a little bit more work that can be done here, because now we have still an x squared back here. That potentially can be factored more. X squared is a perfect square, and 4 is a perfect square, so it is the difference of squares. So we can write this as x plus 2 and x minus 2. And now we have all just as linear factors, just x's, and so that is completely factored. That is our answer. Let's look at number 9. Number 9, we have x to the 6th minus 9. So now I've kind of thrown these a little bit out of order. I was just moving from 2 to 3 to 4 terms. We're back down to 2 terms here. So let's just think about the process of how we would factor. We'd recognize there's no common factor. We do have 2 terms. So it's got to be a sum or difference of perfect squares. X to the 6th is both a perfect square and a perfect cube. X squared to the 3rd power is a perfect square, and then x to the 3rd to the 2nd power is a perfect cube as well. So that doesn't give me a whole lot of guidance, but 9 is only a perfect square, not a perfect cube. And so if I want to factor this, I'm going to use my difference of squares. To get to x to the 6th, I'd have to have x to the 3rd and x to the 3rd. And then 9 is 3 and 3. So remember, we can always check these by multiplying them back together. X cubed times x cubed. We multiply two like bases. We add their exponents. We do get x to the 6th. 3 times a negative 3 is a 9. The center terms are going to cancel. And so that's our answer. So relatively simple. The trick is just recognizing that it is a perfect square. So don't see those higher exponents and say, oh, it's not a square or cube. It very well might be if we can think about what those smaller powers would be. And then finally, number 10. This one may be the trickiest one. We see that we have 1, 2, 3 terms. We only need 1 plus in there. 3 terms, and we don't see a common factor. And it's really, really messy because these x's aren't just an x squared and an x, they're under the cubed root. But we can factor it in the same way. Anytime that I recognize that that middle exponent is exactly half of whatever the one is on the front, that can be factored using these binomials. You can factor into the pair of binomials even though it's not really clean x squares and x's. So if we think about the cubed root of x squared, how did we get that? Well, we must have had 2 cube roots of x's being multiplied together. Sometimes it's easier to think about these in terms of their fractional exponents. I'll clean up that 3 and then I'll write this out. So these are both the cubed root of x. So if we think about it in terms of the fractional exponent, let me write this using those fractional exponents. We'd have 2/3, and then we'd have 3x to the 1/3 plus 2. We can see that this middle exponent is exactly half of the first. Yeah, they're both cubed roots, but that cubed root is going to be kind of the first term. That is going to be what multiplies to give us the squared element of it, that there were 2 of them. And so now we're going to factor it the same way we did before. The factors of 2 are 1 and 2, only possible factors. And then because this sign is positive, the signs are going to be the same. They're both going to be whatever that first sign is, so they're both going to be negative. If we were to check that, we'd have the cubed root of x times cubed root of x, which is a cubed root of x squared. Perfect. And we'd have minus 2 minus 1 cubed roots of x. That's a negative 3 cubed root of x. and then we have a -1 times a -2, which is a +2. And so we have that factored correctly. Just as one last idea on these, what you can do as well, if you really feel uncomfortable with the cubed root, you could replace that with, say, something like y. Let y equal the cubed root of x. And so then I'd have the equation y squared, because it was an x squared cube root under the cube root. Then we have a -3y, and then we'd have that +2. And I think for most people, this becomes much more visually obvious what the factors should be. We'd have a y and we'd have a y. We'd have a -1, -2. But then we'd have to remember that, hey, that y was just something we made up. It was really something more meaningful as the cubed root of x. We'd go back and plug those in as we get to the exact same place. It's the exact same answer. So I think definitely, as long as we can remember the formulas for the sum and difference of cubes, as long as we can remember the formula for the difference of squares, those are fairly straightforward. They're just a matter of kind of using those formulas. You do need to know the formula for the cube or figure out how to derive those each time. For the factoring by grouping, again, as long as we understand how the pattern works, I think that is relatively straightforward. It's relatively easy. The trinomials are definitely the tricky ones, I think, and that is just a matter of trial and error to a certain extent in practice, because the more you practice, the faster and faster you get at them, the more quickly you'll see them. And if you're staring at one of these for 5 minutes, that's too long. You need to be able to generate these factors fairly quickly. I'd say, each one in less than a minute or so. So the more you practice, the more comfortable you're going to get with them. And so it's just the key. Practice until you really feel comfortable, because these are important skills. We're going to use these for as long as math exists. This is going to be an important skill.